Okay, so this is going to be kind of a quick video, specifically mainly for people that were absent due to illness or activities and whatnot. So I have the notes already laid out, and I will have posted in Classroom this video along with a copy of the actual notes so that you can look at it. But you'll probably want to, at least at times, hit pause on the video to kind of, because I'm gonna probably go too fast for you to like take notes as you go. This is more along the lines of just laying some things out and explaining my rationale. The lecture took about 45 minutes, and so I don't want the video to be that long. I'm going to try to keep it down to about 15. So anyway, let's go ahead and see what we can do about that. And so here we go. Let's go ahead and take a look at 2.3b, which again, 2.3b isn't really a section. It's just the way that I kind of catalog it. That's the second portion of our information on that data. So I'm going to move this over here so that my eyes aren't kind of being weird here. But so we're going to go through a couple things. First is the idea of end behavior. Every single time you see that idea of a polynomial or an equation where it says end behavior, what I'm asking you to do is consider what happens as the function either goes to infinity or negative infinity. And so this is the proper notation. You put LIM on top. You say what is happening to that variable. In this case, the variable is X is my independent variable, but it could be Y or theta. You would just indicate what variable you're talking about and where you're wanting to consider that variable. But ultimately, if you're dealing with a polynomial, the thing that you need to look at is the leading coefficient, which is the coefficient on the most powerful term, and whether that exponent happens to be an even or an odd. In this case, because it is an even exponent with a positive coefficient, that means both end behaviors are going up. They're both positive infinity. So as a graph, I know it's going to have this kind of shape on the side, and I don't really know what it's going to do in the middle, but I know it's going to be up on both sides. So with that in mind, if we go to the next problem, notice in this particular case, it is an odd power. That means one is going to be up and one is going to be down. But because the leading coefficient is negative, that means the one on the right, the one as you go to infinity, is going to follow that negative infinity down. And because they're opposites, that means this one is going to be up. So notice positive goes to positive, negative goes to negative. And again, that's the right end behavior, the one that you go to infinity. And for that same reason, because this is a negative in x to the eighth, the one on the right is going to go down and the one on the left is going to match it and go down as well. So both of these are going to be negative infinities, okay? So remember, just watch your notation and make sure your notation fits the way that it's supposed to fit. Okay. Now, I was going to go over a little bit about factoring next. And so in the class, what we did next is we said, okay, so how do you use factoring to find the roots or the zeros or the x-intercepts? Those all mean the same thing. That's what we're going to be doing in here, as well as talking about multiplicity. So a little bit of factoring techniques to know what is happening in these graphs as you go in these interior portions in here. So the first thing is I started with f of x being 12x squared. Now, keep in mind, you always want to look for greatest common factors if they exist. And in this particular case, you're going to notice that everything has a 2 in common. So I was able to factor out a 2. And this is the place where I, this time and this time only, did the diamond method with them, because for some people that really, really helps them, but they sometimes can't remember because they haven't done it in a while. So we actually formally did a diamond problem for the first time this year. I actually normally don't do those, but remember, for diamond problems, we ignore the 2 right here, and we just put the first and the last product here. So 6 times -5, and put the 13 down. And we think of two numbers whose product is -30, but whose sum is 13. And we came up with 15 and -2. And I did that problem on purpose because I wanted people to stop and consider 10 and 3 as a possibility, because you can see how 10 and 3 could make 30 and 13. but it doesn't work. And that's very, very important, that you cannot ever have two answers, or literally only one answer that will work, and they have to be the same. So remember how we did this is you would then take your 6x squared to the top and your 5 in the bottom, and whatever these two numbers are, what it's going to fill in the gaps. So notice I got 6x squared, I got my -5, and these two do make the 13x, but the diamond helps me how to break that 13 up. And then I just looked for common factors, and I noticed that both of these had a 3 and an x in them, and 3x times 2x is 6x squared, 2x times -1. Go through that process, and I was able to factor, and so I knew that I had roots at 1/3 and -5/2. So I know the generalized shape. It's going to be up on both sides. It's going to come through both of those roots like little lines, and we can do that. Second problem that I did in factoring, I looked at this one and I did it because I thought that would bother people to have an 8/3. So I immediately factored out a 1/3, which actually made the numbers nicer. Remember, factoring is dividing. So if you're dividing by 1/3, it's like multiplying by 3. So notice if I multiplied each of these by 3, I would get 8, 6, and -9. And then we did guessing check this time. And I asked everybody what they would like 8x squared to be. And everybody said, let's try 4x and 2x. I asked about the 9. Everybody said, let's try 3 and 3. Turns out those were good guesses. I didn't tell them what to do. That's what they guessed. And so we found those roots again. Now, moving on a little bit deeper into my second page of notes. This is a special case. Now, again, this is a strategy that is an awesome strategy when it works. But again, sometimes you try something and it works awesome, and sometimes it just doesn't. This problem was rigged to do that. So anytime you have 4 specific terms and you look at it and you see no greatest common factor, this is a strategy called factoring by grouping. And what I did is I grouped these two together and these two together. You'll notice I put a little dotted line down the middle. And I looked for these two and I said, well, what do they have in common? And what you notice is these both have an x squared in common. So as I pulled this apart, I took out the x squared that they had in common, and then what was left is an x plus 5. Well, in factoring by grouping, then what you do is you go, well, this one has an x plus 5. So my question is, does this one have an x plus 5 as well? But if you look at how this works out, it does, because if I could put a -3 in front, -3 times x plus 5, in fact, is what we had right here as -3x minus 15. Boom, it worked. So I now have x plus 5 in common between these two sides. And when I took out the x plus 5, I'm left with an x squared and a -3. And that leaves me with my roots of being -5 and plus and minus √3. Again, we sort of know that the graph has in behavior up over here, down over here. It's going to have roots at -5, one at -√3, one at +√3. And so I know the graph is going to do something like this. And that's really what that graph ultimately is going to have to look like based on in behavior and its roots. I don't know how tall or how low it's going to go in there. I just know that's the generalized shape. Okay, last question on factoring. Again, re-emphasizing that idea of looking for greatest common factors. And I noticed that these both had a 2 and an x in common. So if I pulled out the 2 and the x, I got down to here. And then people pretty quickly realized that this would be x minus 7 times x minus 7. Bam. And so what happened that was a little bit different here is we had one root at 0, because notice there is a variable there. It's not a constant, but it's a variable. So at x equals 0, that'd be a root. And there's a double root at 7, which is why we would put a root of multiplicity there. And that means when we do this particular graph, it's going to have a root at 0. It's going to have a root at 7. The end behavior is up on the right, down on the left. Remember, since the leading is positive, it's going to go up with that positive, and then opposites because of odd. And so I know it's going to go through at 0, and it's going to somehow bounce here at 7 and go back up like a little parabola. So we're just getting a feel for what the generalized shape of these graphs would have to be. Now, Roman numeral number 3, getting a little bit further in here, roots of multiplicity, degrees, shape, blah, blah, blah. In other words, let's take a look at everything. Let's do it all. Let's try to graph it, make this thing work. But the difference is, in this case, I decided to hand it to you in factored form. So the first thing that I pointed out to the people is we looked at this thing, and if we were to multiply it out, which I'm not going to do, and then we didn't do that in class either. We just looked at it and said, well, hey, I've got an x squared, don't I? And I got a 2x and an x. Well, putting it all together, then I have a positive leading coefficient because there's no negative when I multiplied that out. And it's going to be an x to the fourth. So since it's a positive coefficient with an x to the fourth, my end behavior would have to be up on both sides. So it doesn't matter if I'm going to positive or negative infinity, the answer is going to go up. So I cheated a little bit and I kind of blended the notations together to say, hey, both sides are going to be up. So I know that. But I also know that I've got a root of multiplicity 1 at 2, a root of multiplicity of negative 5 halves at 1, and negative 6 at 2. Now, again, you're going to see things a little bit quickly here, so I will try to explain what I did. But in class, we had a little u here because we knew about the bounce. We knew it kind of came through here and here because of the shape of these things, but what we didn't know is how high or how low the graph would go. And so what we did is we said, well, let's pick a number in between here, and the class predictably said, hey, let's check out -4. So when I plugged in -4 into here, plug in -4, I get -6, plug in -4 right here, I get -3. Plug in -4 right here, I would get +4, and the product gave me 72, which at first we're like, oh, wow, we can't count by ones because 72 would be really, really tall. It's not going to work very well. But then I said, well, pick a number in here, and everybody said, well, let's try 0. That would be easy. And of course, if we plugged in 0, we get -2. Plug in 0, we get 5, and plug in 0, we get 6 squared, or 36, and holy smokes, that got me -360. So now we had to really think about our stuff. And so we decided to count by 50s. And this is the kind of generalized shape we got. And I want to be very, very clear. That doesn't mean that -4, 72 is the max. And it doesn't mean that 0, -360 is the min. It just means it's probably somewhere near that value. So when I graphed this, I purposely made it not look like the minimum, not because I knew it wasn't. It just, I didn't want to like mislead anybody to think that it was not, that it was the minimum. So that's generalized shape. And what you can see is because these roots are relatively closer together, it didn't go as high, but because these roots are far apart, that's why it went so far down. Okay, last, okay, next question. This is one I had them do. Now, I had them do very, very similar ideas. We knew that based on this negative that it went down here on this side and up here on this side. So again, negative leading coefficient, odd, so they're opposites. I saw a little bounce here at 2 and a little cubic here at 1. And then all we really wanted to do is grab a couple of simple values in between. We don't always pick 2, but in this case, I decided to pick 2 because we weren't doing a whole lot of work. So I just tried -1 and 0, and that allowed me to find a reasonable scale that made sense. So in this case, I just counted by 2s because it just made it easy to fit it. If I did 8, it would be too far up here if I counted by 1. So that's what we did. Last thing, and this was the end of the day, is we talked about what happens if we have a problem where I'm giving you the roots and I'm asking you to recreate going backwards in time the other direction from problem number 3, if you will, or problem number 2 for that matter. So I started with my roots and I wrote my factors, because if factors give you roots, then roots can also give you factors. It's a two-way street. When we multiply 3 numbers together, you usually multiply 2 numbers together and then multiply the third number. Now, you can do this a wide variety of ways. So some people like to write 3x minus 2 this way and use this version, which we call it the area model. But some people like to do it the way I do. I don't do this. I do it over here, and I look for, well, the biggest power I can get is x cubed. And then I look for the x squareds, which would be here and here. And so I got -2 and +6 makes 4. Then I look for the X terms, which would happen here and here. So -4 and -45. And then I look for the constants, which only happen right here. That's how I personally do that. So I look for the biggest powers and I just go down one level at a time and I combine my like terms as I go. But feel free to do this if this helps you. The nice thing about this version is it naturally puts our like terms on diagonals, which can be helpful. So I had them do this next problem as well. We had -1, multiplicity 2, so we multiplied that out. 3/5 right here, so we multiplied that out. And we talked about that and really stopped right here. But I said, what if I wanted to say, instead of finding a polynomial, what if I said I want to find the polynomial that specifically goes through 2. So if I wanted to specifically hit this number and I plug in the number 2, what's going to happen is it's not going to go through this route right here, because 2 cubed times 5 plus 7 times 4 minus 2 minus, it's not going to be equal to the number 2. In fact, it's way off. So what I did is I said, well, I put a number in front called k, because as it turns out, k is a stretch factor. So the roots wouldn't change. It would just make the graph taller or shorter depending on what k value I pick. Remember that front numbers multiply the y value. So I went into here and I plugged in the number 2 right here. And 2 plus 1 is 3. 3 cubed is, 3 squared is 9. I plugged in the number 2 right here. 5 times 2 is 10. Minus 3 is 7. And I said I would like this product right here to be 2. And then I did a little bit of mathematics and I found that if I could have a leading coefficient of 2/63, then that would actually force it to go through that problem. And therefore, instead of a polynomial, it becomes the polynomial that goes through those values. So hopefully that is helpful, giving you a little bit of a synopsis of what is happening. And then the homework is literally to just do section 2.3 out of the textbook. Hopefully that was helpful. And I will see you guys back in class. Hopefully those of you guys who are gone for being sick will feel better soon. Bye-bye.